And now in your textbook, this is chapter 10. Some things about your textbook. Your textbook has everything from grades 9, 10, 11, 12 pre-calculus that you need to know for your exam, that you need to know for your labs, is in the textbook as well. So if you're having trouble with sequences and you want to look at where, and you've lost your grade 11 notes, right? Or Ian stole them. Something like that happened. You can look in your textbook in the sequences part. So there's questions from previous units in there of the stuff that is covered by the IB exam. Not everything you've learned already will be on your IB exam. For example, from last year, do you remember doing like permutations, combinations? That's not on there, but the binomial theorem is. So you still need to know combinations, but not, you don't have to know, for example, what would be a typical, there are 5 blue marbles, 4 red marbles, and 2 green marbles. How many ways can you arrange them in a row? That kind of question's not on your exam. So chapter 10 in your textbook is called Bivariate Analysis. It is looking at relationships between two things. Okay, so when looking at this graph, okay, sorry about that. So it talks about a relationship, and sometimes there is a relationship between things that we kind of notice. Like, oh, in this relationship example of a husband's age and wife's age, it seems to make sense that this would be the relationship. What do you think if I all of a sudden put a dot here? Ooh. Right? Or it only goes to ooh. What does that mean? That's a big age difference. And then we start to feel like that would be weird. Okay? Like, if I turn 75 and I marry someone who's 30, my goodness, they would be born this year. Ooh, right? That's just kind of, but it doesn't seem, it's not perfect. It's not like, oh, 2 people can't get married because they're 2 years apart. That's not allowed anymore. That would be also strange. Okay, so we have a relationship that occurs here. We always put an independent variable on the x-axis, a dependent variable on the y-axis. Sometimes, like this one, it probably wouldn't matter which one was dependent and independent. And if there's a relationship between them, which this one seems to be, then we say there's a correlation. Three possible correlations. Do you want to use this stapler? Is really, or that one would work too, but this one like fires it in.
Oh yeah, watch out, watch out.
You can actually shoot students. Don't point it. That's dangerous.
Those are just in a box with
Okay.
essentials books.
Perfect. Okay, so if the dependent variable increases as the independent variable increases, we call that a positive correlation. Here is a very typical example. The longer you work at something, the higher your income gets. For teachers, sounds dangerous. For teachers, this is especially true In the first 10 years of a teaching career, you get a raise every year. And then in 11th year, they say, too bad, so sad, no more raises for you. So you plateau as far as your raises go. And then they only give you contract negotiation raises. So then you still make a little bit more, but the contract negotiation takes into cost of living. I don't know if they're going to do that next time because inflation's been crazy. So that would mean that technically they should be raising everybody's salaries to compensate for inflation, but we'll see what happens with that. Okay. Negative. If the general trend is going down, we call it a negative correlation. So if the dependent variable decreases as the independent variable increases, okay, does it make sense that the higher elevation you go, the temperature goes down? Right? That's why there's no summer vacation spots on the top of mountains. And sometimes there is no trend whatsoever. So here they have the day of the year, and somebody's, what does that say? Something number? Can you read it on yours? Draft number? Ooh, if you got drafted into the army, like what is happening in Russia right now? They're doing a draft. Anybody been paying attention to the news? And now a bunch of people are fleeing Russia to Georgia because Georgia doesn't require visa requirements. It's a crazy world. Okay. So sometimes we have no trend. So what I want you to do for each of these is, if you can, sketch a little graph. The distance from school and the time that it takes to walk there. Does it make sense that the time is dependent on the distance? Okay? I drew an outlier. It's like, this point really doesn't make sense. It would be like if I suddenly had the ability to teleport, just like instantaneously travel very fast, very short distances. So would we call that a positive correlation, negative correlation, or zero? We would probably call this one positive. So think through them all on your own. Draw a little sketch, scatter plot, and then try to think if it's positive, negative, or zero correlation. All right, let's see how we did. Oh, I should have paused the video. This one would be 0. The room number has no thing. Amount of gas in the tank and the distance a car traveled. So gas would be dependent on distance. The farther you go, your gas should go down. Wouldn't that be nice? Oh, I went far. I have more gas in my tank. So that would be negative. Number, I talked about this one, but I talked about the plateau. Oh. At 10, 0. Well, this one might be a little bit, but probably some positive relationship there. You attend class tends to be help you understand the material, right? Ask a friend of yours to do the IB test who's not in this class at the end of the year, because they will have attended not at all. How do you think they will do? Very well. How to draw a scatter plot, pretty straightforward. You set up your axes. You write a title and units. When we choose our units, we choose an appropriate scale, okay? So you can't be changing, like go by 10s, then go by 2s, then go by 20s, then like your scale goes the same all the way through. Sometimes, for example, if I wanted to show data from the year 2000 to the year 2003, and I had data points, I probably wouldn't do this. 1,000, 2,000, and then I'd have, here's my, like, this is wasted space. So sometimes we have, when we draw our graphs, sometimes we like add a little break in the graph so we can say, I'm starting with 2,000 here, and then 2001. It didn't make sense for me to include stuff prior to that. So you can do stuff like that as well. Write a title for your graph, independent on the x-axis, dependent on the y-axis. There we go. If you get a table of values, the first column is always the independent data. We also talk about strong or weak correlations. If you drew a straight line through the data, all three of these have a similar positive correlation. But we would say the first one is stronger because it's closer to the line than the last one. We would say that that's weaker. And so we're going to come up with a way to measure how strong or how weak something is. And same thing with negative correlation. This one we would say is strong. This one we would say is weak. If it gets so weak, it gets closer and closer to no correlation whatsoever. And there are also some correlations that can be strong, but they don't have to be straight lines. So we're going to do a bunch of math with straight lines, but there are sometimes data points that follow a different curve. And so you can have correlations that are linear. You can have correlations that are quadratic. This would be, looks almost logarithmic. And one of the reasons that we start with statistics and we start with information like this is some of you are going to choose for your internal assessment to collect some data and look at that data and look at the equations. And you might say, hey, I think my data forms a parabola, and I want to find out the equation for this and see how well it predicts my data points. Did I give you space? Yes. So, decide on your own scale to draw this. Do you want to do that? Like, is this easy? Should we skip this so we move along faster? Like, could you pick a little break in there and draw dots? You think you'd be okay with that? Okay. Would you say that this has a strong negative correlation? Are you okay with not even copying it? If you needed to look at it online, you could. Like we'd rather spend our time thinking about more complicated stuff rather than not as complicated stuff. Oh, look at that wonderful title I came up with. Like so. So the first mathematical thing that we're going to start to try to figure out is to try to find the line of best fit, or trend line. Weeks of practice and the amount of words per minute that you can type. The more practice, the faster you get to type. So it makes sense, right? But sometimes you have bad weeks and you just can't. Or there's tough words that you have to type. Exercise, kilometers you run per week, and weight, well, nice little outlier out there, right? This one, is this one person's weight? Is this a whole bunch of random people? There's going to be different things in here. You can see why this might not be as much of a correlation, but we want to find the line of best fit. And then the question becomes, well, how do I know this one isn't better than that one? So some observation things, some common sense things. Can you see that the one that they've drawn would definitely be better than that one? Because as far as average stuff goes, we have some above and some below. So we want to have approximately the same amount above as we do below. But then the question is, well, what about that one? Why isn't that one, which one's the best? And that's what we're really trying to find, is the line of best fit. So our first attempt at the line of best fit, okay? If you're doing it by eye, we want to find the average of your x values and the average of your y values, the mean of your x values and the mean of the y values. Does it make sense that that point should probably be on your line of best fit? Okay? And then once you have that middle point for your x and your y values and you plot it, then if you draw the line, you want approximately half to be above the line and half to be below the line to see what it would look like. So here's an example. Hope this doesn't make you too hungry. Bunch of different sandwiches from different fast food places. Total grams of fat and total calories. Is there a relationship between how much fat was in the sandwich and how many calories were in the sandwich? So you could add up all of the x values and divide by how many you had, add up all of the y values and divide by how many you have, and you would get the average of the x values, average of the y values, so we could say that our mean point is 22.3, 453. Then again, if we drew all the data points created a scale, drew the data points. It sure looks like there is a positive correlation here. And then if I label that mean point, maybe, whoa, that's fancy, whoa. And then I tried to draw, I'm kind of thinking maybe I should have tilted it a little bit more this way. I tried to make half of them above and half of them below, going through that average. But that gives me an estimate for my line of best fit. So then if all of a sudden someone said, welcome to the Energy Burst burger, 1,000 calories in one burger. And you were like, whoa, how much fat would probably be in that burger? We could extend this line up to 1,000, go across from 1,000, just like we were doing with our cumulative frequency graphs, go down and go, ooh, that's like my week's limit of fat intake in the one burger. Oh, sometimes restaurants have things like that. If you finish this meal that we give you, then it's free. If you don't finish it, it's $150. And they bring you a burger this big, and no one can ever finish it. But people try. And then, is that dangerous, right? What happens if you forced a person to try to eat way too much, and then they had some sort of medical emergency? Then are you liable? I don't know. Another word for the line of best fit, also trend line, is the regression line. And here's some definitions that you learned, well, they're in the grade 9 curriculum. Do you remember the word interpolation? Well, in French it would be very close, but with a French accent probably. And extrapolation? If you interpolate, you're looking for an estimate from within the data they have, inside. And extrapolate, if you think of extra as outside, that's when you find information from the outside of your data point. So if you wanted to find an actual algebraic equation of a line of best fit, so if we go back to this one that we figured out, you would know that it goes through this point, because that's your average point. It for sure goes through there. And then if you pick one other point that your graph goes through, let's say I chose this point, can you see that you could then use rise over run to get the slope? And then you could write your equation in y equals mx plus b form. For equations of lines, do you remember the y equals mx plus b? Do you remember the y minus y1 equals x minus x1 formula? No. Some of you are like, maybe. I would say Mr. LaFrance uses that equation just a tad bit more than I do. So, but it's this equation technically, do you know that this is how it's really easy to remember this formula. You know how slope is the rise over the run. And rise is the change in your y values. So if you took a random y value and subtracted a specific y value, and took a random x value and subtracted a specific x value, this would be your slope. Taking your slope formula and just getting rid of the fraction, gives you that formula. So it's just your slope formula rearranged. The nice thing about this formula is you just need a slope and any point, and then you can rearrange it. With this formula, if you have a slope and any point, you can plug things in and find b and then write your formula. So they're both really helpful. Typically, as you move higher on, you tend to forget this one. Something about y equals mx plus b sticks in your head, and you remember that one for a long time. Okay. Here is a good hypothetical situation. A bunch of students had term marks in this class, and then they wrote a final exam in this class, and this was the final marks of the student. But Ian strategically got COVID during the exam. Oh, so sad. I don't have to write it. Okay, no, let's not go strategic, because then there might be a feeling of like, that's not fair, that everybody else had to work. But Ian's okay, but was struck by a bus 20 minutes before the exam. Everything is fine. He just, yeah, no broken bones, but you were knocked out for exactly the amount of time that the exam happened, and no long-term. We have to make this positive, right? Struck by the bus was really harsh. Yeah, he's fine, but he missed the exam. But he studied just as much as everybody else. What should happen to his final mark? Okay? Well, sometimes what typically happens in this situation in a school is the student gets the mark that they had going in. But is that fair? Right? If the exam was really easy and everybody's mark went up 10% in the class, Ian would feel like, I was ready for that exam. That's not fair that I have to stay at an 80 and everybody else's marks go up by 10. Okay? If the exam was super hard and Julia's like, all of our marks went down 20%, that's not fair. I mean, I feel bad that he got hit by a bus. But is it fair that at the awards ceremony, Ian gets the new $10,000 scholarship for IB Math final grade because he didn't write the final exam and everybody else's marks went way down? So maybe we would have to do some sort of way of figuring this out. So of the 9 students that were there, the mean point is 75.72. We could take this data, draw a scatter plot, put the mean point on there, draw a line of best fit, where data points are above and below, and say if Ian went in with, according to this graph, if Ian went in with an 80, we should have his final mark be a 76, to be fair to all the other students. But that's a hard argument to give, right? Because studying is an individual thing. And so that's why schools tend to, when students get hit by buses and get knocked out for exactly the time that it takes to write the exam, they tend to give them their mark that they went in, because it has the least amount of controversy. But you can see in the scenarios that I gave where, like if the exam was really easy and everybody else's marks went up, then you would feel like that's not fair. Or if the exam was super hard and everybody else's marks went down, from another perspective, that's not fair. So Here's another idea, using a line of best fit to see this is what should be a way of looking at it. Now, if you wanted to find an equation, you could take 2 points on the graph. I happen to say, according to the picture that I drew, I've got my mean point. That one was right here. I took another point that my graph went through, 80, 85. And based on that, I got a slope of 1. I could then either use this equation or this equation to find out my actual equation of that line. If you're using y equals mx plus b, you would plug in 1 for m, because you figured that out, plug in a point that you know, which is your mean point, and then you could solve for b. If you use the other one, you plug in the point that you know and your slope right away, rearrange it, and you get exactly the same equation. Then we could use that equation to say Ian's mark should have been a 77. It looks like on average people's marks are going down by 3. That would be an interesting scenario. We use last year's exam to say, last year's students, everybody's marks went down 10%. Do you want to accept that and not write your exam? Or do you want to see if you can do better than that? No, I don't think that would be allowed either. So, in a line of best fit, what does the slope actually mean? And there's lots of questions that say, what does the slope mean in this example? Okay? Well, slope is rise over run. And when slope is just a number, so even if it's a decimal, right? If I get my slope is 3.7, that's technically 3.7 over 1. So I still have a rise and a run. And what it means is that the 3.7 is how much the y value increases for every increase of 1 for your x value. When your slope is a fraction, right, this tells me that every time x increases by 3, y increases by 4. That's what the rise and the run says. But often, this would just be reduced to a decimal. And so now it's saying that every time x increases by 1, the y increases by 1.3 repeated, which is the same answer as the 4/3, just said in a different way. And so it's very typical that our slope is written as a number, and so then the x is increasing by only 1 unit. The y-intercept. The y-intercept value is always the value when x is 0. And typically, in a graph, that's kind of like a starting point. Lots of graphs have time along the bottom, and so time being 0 is where you started from. All right, so we can have so much fun with these studies. Study in the relationship between the age in years of a young person and the time it takes in minutes to run 1 kilometer. Okay? I don't know whether this would pass ethics protocol if you were doing this study now. Hi, 5-year-old, run. And then you just time them until you get back home. Not sure. Okay? So they've got data. Oh, they only started with 7-year-olds. 7-year-olds to 18-year-olds. And the equation was found to be 20 minus 1/2 x. Can you see that you could rewrite that as 1/2 x, negative 1/2 x plus 20, which is in your y equals mx plus b form. Okay? So your slope is negative 1/2. Your y-intercept is 20. What does this mean? So you have to figure out what is the relationship. X is the age. Y is the time in minutes. So what does a negative 1/2 mean as a slope? That means the y goes down by 1 every time the x goes up by 2. So x being age, every time you increase in age by 2 years, the time in minutes should go down by 1 minute. If you reduce that to a decimal, that becomes negative 0.5. That means every time the child's age increases by 1, their time would reduce by 30 seconds. Okay. Y-intercept. Babies take 20 minutes when they're freshly born to run a kilometer. Have you ever seen a baby run a kilometer? It doesn't really make sense in this question. So we run into, sometimes we might have a line of best fit that works well for some things, but some parts of it don't work well. Okay? I like this equation because I can put in my age and it takes me minus 5 minutes. I just ran a kilometer. You just missed it. To run a kilometer. So it obviously doesn't work when the numbers of x get larger, and it doesn't make sense when the numbers of x are like 0, 1, or 2. It might, though, make sense for children aged 7 to 18. Maybe this is actually a proper model for that, but it doesn't make sense. So we would say you could use this data to interpolate. Maybe it works between ages 7 and 18, but you can't use it to extrapolate. That beyond 18, you sort of plateau or you get slower. And babies can't run. Can you imagine the same person doing the study? They plop the baby down, start their timer, and say, go. How many years would it take before that baby could run that kilometer to end the study? So, does the number of trees affect the number of birds? We've got a regression line calculated to be y equals 5.4x plus 8. So your slope, change in your y values. So every 5.4 trees per hectare. No, y is birds. For every 5.4 birds, you would get an increase of 5.4 birds for every increase in 1 tree. So you increase by 1 tree, you get 5.4 more birds. Have you ever seen 0.4 of a bird? Not pretty. What does the y-intercept mean here? Okay, y-intercept is when x is 0. So if x is 0, meaning that there would be no trees, Is it still possible to see 8 birds? Maybe, right? They could just be like flying through. Trying to think, where are there places in the world where there are no trees? And are there lots of birds? The middle of the ocean, there are no trees. In the middle of the ocean, I don't think there are birds. I guess some of them might be, but do some birds fly across the ocean? Do they migrate? Do they go across the ocean? Or do they just go like south? These are